All right, hey guys. So far we've talked about an incredible amount of processes that happen on Earth, specifically, of course, relating to oceanography. But now we're actually going to talk about, well, where did Earth come from anyhow? So this is all about Earth's formation, right? To understand how all these processes work, we have to, see how this stuff actually got there. So I'm actually standing out in front of the Rhode Island Nuclear Science Center. This is the only operating nuclear reactor in Rhode Island. You can see it's a big gray building. There we go. And inside is a 2 megawatt nuclear reactor. So I'll tell you what, let's go inside and see if we can't tackle at least that first question. Where did those atoms come from that we've learned so much about? So I'll see you guys inside. All right, guys, and here we are in the control room at the Rhode Island Nuclear Science Center. That is the nuclear reactor back there behind me. And you might notice something a little bit different in this video today. Normally, I do these things by myself, but today I have a guest. This is Froyo the Wolf. You want to say hi to everybody, Froyo?
Hello, everybody. I'm Froyo.
And Froyo is actually a student there at CCRI, and he's studying nuclear power. Specifically, he's studying this reactor.
Oh, yeah.
And so he's here today to learn a little bit to help him out. And the reason we're here is, like I said, this is a 2 megawatt nuclear reactor. And what that means, just to give you guys a perspective of how much power that is, this thing could power like 4 refrigerators for a year.
Wait, so what are you getting fridges from?
Well, that's just an example. I mean, it just...
No, this doesn't produce electrical energy. It's thermal energy, actually.
Well, okay. Sorry, yes, it is thermal energy. I'm just trying to make an example. Okay, this is why I tend to do these by myself, because nobody corrects me. But anyhow, Froyo's right. This is a thermal energy reactor, that 2 megawatts. So, with efficiency, if you could produce electricity, it'd be something less. Say you could, toast 80,000 slices of bread. How about that?
Yeah, you could have bread if it was efficient and if it produced electrical energy.
Okay, but it can't. So anyhow, some reactors can. So in fact, in the United States, we've got about 96 operating nuclear reactors that actually do power things. And those megawatt ranges are a bit higher. They're up in the smallest one's a little over 500 megawatts, and that's actually electrical power. Thank you very much.
Well, you're welcome.
The biggest one is quite a lot bigger, in the thousands, multi-thousands. And those power whole cities, right? So this one is just used as a research reactor. It produces heat. It doesn't produce electricity, but that's okay. We'll move on from there. But what it does do, okay, is it answers our question. And that question I had from you was, where do we actually get these atoms from? So we know where the compounds from life come from, right? The things that make Froyo and make you and I. And we want to know where those atoms come from. Where do we get these carbon, hydrogen, and oxygen that's in glucose? Well, if you remember, all those atoms are made up of neutrons, protons, and electrons. So we can mix and match them. And things like this reactor can take smaller atoms and make bigger atoms, can make some of those things up.
You got it backwards. This doesn't build them up, it breaks them down.
Well, what do you mean?
It takes the bigger stuff and breaks it down into smaller stuff.
But like plutonium or?
No, not plutonium, more like uranium. Like uranium-235.
Okay, yes. Yes, okay, this is a fission reactor. This is just going to be an example. Okay.
Well, you got to make sure the examples are right, man.
I know. Okay, so this is a fission reactor. So it can take things like, yes, uranium-235. And because those big atoms on your periodic table are so big, there's so many neutrons and protons in there, they're a little unstable. So what we can do is take another neutron and shoot it into that atom, sort of like a gun. And what happens is it becomes so unstable that it breaks apart, all right? And it turns into smaller atoms. And yes, that is called fission. So,
oh yeah, these things have mental and emotional breakdowns, just like me.
Yes, they do. I think everybody's a little stressed right now.
Oh yeah.
Including nuclear reactors. So yes, that's what happens, is we take bigger atoms and make smaller ones. However, there are places that do something called nuclear fusion. And that's where smaller atoms are taken to make big ones. So again, just combining those neutrons and protons and electrons. So the reason we have this array of atoms across the periodic table is because out of something we'll talk about here a little bit later, at the beginning of the universe, started with the smallest atoms, right? It started with helium and hydrogen and a little bit of lithium. So if you go look at the periodic table, those are really small. But then what happens is they can combine. So in fission, we're going to get power, okay? And that happens because if you take that uranium-235, right, and split it up, well, what happens, let me ask for you, what happens if I add up the masses of what's left over and compare it to the mass of uranium? How about that? Do you know that?
You throw it all into a big bowl, you mix it up, and you get a cake.
Okay, the cake is another picture, but that's fine. All right, what happens is there's a difference in mass. All right, so uranium is actually more massive than its parts. But the neutrons and protons equal each other. Why is that? Well, how about this? Do you know who Albert Einstein is?
Oh yeah, he's the guy with the big white hair who stuck his tongue out for a picture.
Actually, that's very true. He did do that. You guys should look that up. It's pretty good. Do you know what he came up with? A famous equation?
E equals mc squared.
Okay, so you do know that. All right. Well, fine. All right. So E equals mc squared. You guys may have heard of it. Well, what it is that E is energy, that big E. And when he figured out a very simple equation is if you take that mass, that very tiny difference in mass between a big atom and smaller atoms, and you multiply it times what?
The speed of light, but squared.
Yeah, so a big number. You get an incredible amount of energy out of a very teeny tiny bit of material.
Oh my gosh.
And that's where we get this from, all right? Now, on the other side, you also can get that kind of energy out of fusion. So the same thing, you take, a couple hydrogens and you make a helium, right? Because the neutrons and protons add up, but you're still left with mass. In fact, do you know something that you use every day that is powered by hydrogen?
A spoon.
No.
Oh. A hot air balloon?
Something you see every day. Well, maybe not today because it's kind of rainy out.
Oh. Wait, are you talking about windmills?
Not windmills, that's wind energy.
No.
It's big and bright in the sky every day.
Oh, studio lights. Bright light.
Studio lights, the sun, right? Of course, the sun. So the sun is powered with this fission energy. It can take hydrogen, two hydrogens, smash them together, create helium, and get all this energy. However, there's something else going on. So we've already talked about energy that binds molecules together, keeps atoms attached to each other. We get a lot out of that. That's how we can oxidize glucose and get energy. But there's even more energy trapped inside individual atoms. It's something called binding energy. Now, you guys already know that protons are both positive, right? So the overall charge in the nucleus of two atoms is positive. So they're not going to want to touch, right? So like if you take two magnets and try and squish them together on the same side, they're not going to meet.
Or getting two siblings to get along.
An excellent example. So how do you get two siblings to get along? You got to get somebody to come and just put their heads together, right? And make them, shake hands and make up.
Yep.
And what happens is if you can get them close enough, another force takes over. And that's something called the strong nuclear force, or just the nuclear force. Now, when I say closer, I mean about 10 to the minus 15 meters. So really, really close.
They're smaller than my nose hairs.
It's only a little bit smaller than your nose hairs. Your nose hairs are pretty small. We have some special effects in this video. If you guys have ever seen Tom Cruise stand on a box, we sort of have the same thing going on. But anyhow, what you can do is once you get them close enough, that force takes over and will make them stick together. So those two hydrogens will come together and make helium. But you need some incredible amount of energy to get them close enough. And that's where things like the sun comes in, right? They're so massive that the gravity of the sun can push those atoms close enough to where that happens. So in all of our stars, you have the power from them is coming from the mass making gravity pull everything together like we know it does, and then these nuclear reactions pushing everything apart. So all of our stars are in this constant flux of gravity pulling things together and nuclear reactions pushing it apart.
So, wait, all of our stars are just continuously trying to themselves up?
I guess that's a less eloquent and life-giving way to look at it, but sure.
I thought I had a difficult life.
Yeah, it's not great. I wouldn't I guess want to be a star, maybe a YouTube star. Froyo's a YouTube star. I'll tell you about that in a little bit. Anyhow, so what's happening that whole time is that push and pull, right? And since the beginning of the universe, we're creating bigger and bigger atoms with this power. Now, something like our sun is only creating helium out of hydrogen. In fact, it's creating like 600 megatons per second. That's about 19,000 super tankers worth of helium every second.
That would be so many balloons.
That's a lot of balloons. That's a lot of helium. Now that I think about it, and I don't know why the sun's not very high pitched, but anyhow. So that's our sun, but that's a small atom. So it's going to take something else to make these big ones. Things like much bigger stars or supernova, these giant celestial explosions are creating these atoms. So now you guys know that's why we're here in this reactor. We're talking about nuclear power, and it has everything to do with the beginning of the universe, right? Where all of this stuff comes from. So now we're going to go back in and we're going to take that information and we're going to figure out your second question, which is where the Earth came from, how all this happened in the expanse of time.
Oh, I thought it was, why isn't there any milk in my fridge?
Anyhow, so what we're going to do, I'd like to thank Froyo for being here with me today.
Well, thank you very much for having me.
Hopefully, well, I would say hopefully you learned something, but I'm pretty sure I learned something.
Oh, I learned so many things. I learned about toast and fridges and cows and blowing yourself up. It was so educational.
I really hope you guys took some other stuff away from this today. With that said, also make sure you check out Froyo's YouTube channel. You can find it under Froyo the Wolf. And I'll see you guys back here when we'll talk about the universe and everything. See you.
And everything. Bye!
Nothing. No time, no space, unimaginably nothing. And then in a single instant, from a single point, everything, all the matter, all the space, and all of our time, what we call the universe, became into existence. In a fraction of a second, protons form. And in less than 2 minutes, the hydrogen and helium and a little bit of lithium form from nuclear fusion. And then if we fast forward 13.7 billion years, we're here, we're now, right? All of the things we've been discussing, all of the oceanographic processes, and really all of the world processes are because of that first instant, right? Some of you may know this, something called the Big Bang, all right? So what we want to do to figure out, how we got here and why all this stuff works the way we do, we need to go all the way back to the beginning. And I told you guys at the beginning, the beginning of this class, I really meant the beginning of everything. Before the Big Bang, there was no space. Like, to ask what happened before the Big Bang doesn't make any sense because there was no time, all right? And that's almost impossible to wrap your head around. I can't wrap my head around it. I think about it all the time, oddly enough. But we're going to try. We're going to try and just say, okay, we're going to start there, and then we're going to move forward. And I'm going to create a timeline. Like I said, it's, 13.7 billion years, right? Clearly a lot has happened. And surprisingly, most of the stuff we want to talk about is relatively new. And you'll see what I mean here in a little bit. So let's say I'm going to create a timeline, all right? And over here on this side, we'll say this is the Big Bang. This is the start of it all, the start of time, the start of matter, our whole universe. And over here, all the way on the right, is now. So let's put up this timeline, and each one of these numbers is 1 billion years. Now, I don't know how big your TV is or the screen you're looking at, but let's just, for argument's sake, so we can make some analogies here, let's say every 1 billion years is a foot, all right? So 1 foot equals 1 billion years. And you'll see here we go almost 14 feet, right? I said about 13.7 billion years, which means every inch is about 83 million years. And I'll come back to that, and we'll use that for something as we go along. But let's just talk about a few of the things that happen along the way. Okay, so we already said, over here at the beginning, less than a second, again, like 10 to the minus 6 seconds. So 6 zeros or 5 zeros and a 1. That's how fast protons formed. And then in less than a minute, that hydrogen and helium. So that nuclear fusion process that we talked about, hopefully I didn't confuse you in the beginning between fusion and fission and all that stuff. The big thing to take away there is nuclear fusion will create these atoms. So that's what we get, hydrogen and helium, and like I said, a little bit of lithium. Well, in about, 500 million years, okay, So let's be fair. For like 100 million years, it was just dust, right? Dust and gas before we even got stars. All right, that's for about 100 million years. And then about 500 million years, we get our first galaxies. Fast forward a little bit, all right, so about 1.2 billion years, we get our galaxy, the Milky Way. Not in the form that we know it now, but we do get a Milky Way galaxy. And then we move in this area, just galaxies start forming, right? Now we're billions of years. So let's go 3 and a little bit billion years, and we get peak star formation. So between like 2.5 to 4 billion years, this is when the universe is really cranking, really making stars. And if you guys remember, stars are what are making more elements. So this is why this is important. This is where all this stuff comes from. We started with hydrogen and helium, and it's these stars that, because that gravity, because they're so massive, they can get those other atoms close enough together where that nuclear energy takes over, or that nuclear force, to where they stick together and form new atoms. So anyhow, this is that peak star formation. And this is also where habitable planets start to form. So the possibility of things that could have life. 3.5 billion years. Now, this is 10 billion years before now. So this is pretty substantial that this has already started to happen. And then pretty much not a lot. So from about here to here, okay, this is all that's going on. Stars are forming, stars are exploding, supernova, more elements for, what's that? 1, 2, 3, 4, 5, 6 billion years until next thing I'm going to talk about, I mean, there's other stuff going on, but about right here is where our galaxy becomes a spiral. So it took that long. So here's where our galaxy began, the Milky Way. And in about 7 billion years or so, if my numbers are right, it finally looks like it does now. So that's pretty amazing. So that's where we live, in that galaxy. And then you go a little bit further, and this is where it starts to get important to us, is a little over 9 billion years. So I'm gonna sort of switch here. I'm gonna start talking backwards. So this is, say, 4.6 billion years before now. So remember, now is right here. So let's start talking about what happened before. So a little after 9, that's 4.6 billion years ago, we get the sun, we get the Earth, we get the moon. Not all in an instant, there was some millions of years, but effectively that all happens at once. Our solar system comes into existence. And a little while later, okay, about 4.4 billion years ago, we get our oceans, all right? And again, this is oceanography, and that ocean has been around for the vast majority of our planet's life in about 4.4 billion years. And then there's this area right here, and this is where life happened. So why are we talking about this? Well, we talk about life, what's required for life, where it came from. Well, in time, this is about where it was, okay? And it's, we don't really know, so there's a pretty big span there. So like I said, there's, about 500 million years or so where we're not really sure, but it's somewhere in there. And then life just kind of hung out. Microbiology, right? These tiny little organisms, bacteria and archaea, and these minuscule little organisms just kind of hanging out. Taking some chemicals and turning them into others, using these processes, not cellular respiration like we know it, because there was no oxygen yet, but some of these other processes, and they're just kind of hanging out, all right? So it was a little bit boring here. And then, some of these organisms start doing photosynthesis, and they start producing oxygen. And then about right here, about 2.5 billion years ago, we have oxygen. This is a great oxic event in our Earth. And after that, right, we can start having bigger things, because as it turns out, that cellular respiration using oxygen is really energy intensive. You can do some amazing stuff with that. So soon after that, we start getting multicellular life. So, 500 million years later. So more than one cell. So again, life started here, and it wasn't for 2 billion years until we get something more than a single cell life. And then another period of sort of boring. And this is actually kind of known as a boring era. Everything's really small. Again, turn in some chemicals into others, but nothing that you would call amazing life. I think if you walked around, you probably wouldn't notice anything. Some, mats of slime maybe around, but that's about it. And then something truly fascinating happens on our planet. At about 540 million years ago. So again, really close to where we are now, we get something called the Cambrian explosion. and it was just an explosion of life. In the fossil record, it's just like life happened, okay? And then that's when a lot of interesting things happen. So I'm just gonna kind of star this here because I can't really put any more arrows. So the best I can do is, I said I'd come back to that analogy of time. So 83 million years, as I said, was about an inch. So, about that far in my hand. So we'll say that this is now, right? Okay, so the end of my hand is now. And if we go back about 5.5 inches, so 450 million years, so about here, that's when we get our first land plants. So we didn't even have land plants until then, all right? And again, if you're trying to do this and figure out on your own hand, just remember that the beginning of the universe is 14 feet away that way. So not even on this camera. In fact, the Earth, what is that, like 4.6 billion? That's like 4.5 feet. That'd be like my watch from here. I can just get that on the screen. That's like the whole history of Earth, and the land plants were here, right? And a lot of other things happen as we start moving forward. So, 5 inches, we get the first air-breathing animals. So the first animals to breathe air that, again, is a gas, not necessarily in the water. About 1.5 inches, flowers, flowering plants come into existence. Some of those vascular plants that we talked about. And there's a lot of other stuff. I'm not going to go into all of these, but just a couple to give you reference. So how about dogs? All right, let's get really small. When did dogs come around? Well, that's actually going to be something like the thickness of a red blood cell in our time analogy. All right, or recorded history. That's like the thickness of a bacteria. And your life is about the thickness of a virus on the end of your finger, and that's about it. So if you ever thought and looked out in space and thought, wow, I'm really not very significant in the world. Well, I would say that all of you are significant in one way or another, but if you're trying to compare yourself to the rest of the universe in time and space, yeah, probably not. So let's not do that. Let's not get too much into our head there, especially with everything that's going on. We got enough to worry about. Let's stick to learning, right? So that's where we are. This is why we're showing this. Where did everything come from? Because we want to answer how the Earth got here. We now know how these atoms actually arrived. So again, this whole time up until the Earth, bigger and bigger stars are making the heavier elements. So like I said before, our star is only making helium. It's not actually that big. The gravity's not enough to make more things. The heavier ones come from supernova, these massive explosions that can actually pull larger nuclei close enough to make bigger elements like iron. And that's all happening here before we get our planet. Because importantly, when our planet formed, we had all this stuff. All the stuff that we've talked about was already there, so that had to happen before. So how did we get there? All right, let's move on from here. We get to our planet. Let's talk about just this area, how we got a planet. Well, like I said, for a long time, there's just a bunch of gas. So our Milky Way galaxy finally forms a spiral, and all this stuff, because of gravity, starts to accumulate, all right? And you get, it's spinning, and you get something like this, right? Just a bunch of stuff spinning around its own gravity, all right? And as it keeps moving around, gravity starts pulling the larger clumps together more and more and more, and it starts to resemble a disk, all right? You start to get this center of, really dense stuff in the middle. And because it's spinning, sort of the same mechanisms we talked about, inertia and gravity working together, it starts to form a disk. Well, as you might have guessed, the center of that disk becomes a star, all right? It becomes our sun. And then around our sun are more disks of stuff, but they start to clump together. You can start to see some of the bumps here. And eventually, more of this clumping, right? We get our solar system. We get just like the heavier stuff in the middle, right? Our rocky planets and our sun. And then as you get to the outside, we get the lighter stuff, outside the asteroid belt, Jupiter, Saturn, right? A lot of those gas giants. Well, this is how we got our Earth also. So, we're up in this stage here, and somewhere in between here, right? We start to get our Earth. Where's Earth? There it is right there. And that stuff starts to form together. And this is something called accretion, all right? So this is an accretionary disk. Accretion is just that clumping of elements based on gravity, right? They start to come together, and the same thing happened with our Earth. And when our Earth clumped together and started to solidify, we get something else happening, something called density stratification. So again, gravity's pulling all the heavy stuff to the middle, and all the lighter stuff is moving to the outside. All right, it's just gonna keep happening over really millions of years. Well, eventually, with all this density stratification, all that heavy stuff going to the middle, and all the lighter stuff coming to the surface, well, just like our atmosphere and just like our oceans, our Earth becomes density stratified and we get layers. We get something like this. From the heaviest stuff here in the middle, all the way out to the lighter stuff here, where we live, where our oceans are, where all the life that we know of exists. And that's how we got there. But how do we know this? All right. So how do we know that there's layers in the Earth? And now this is kind of a neat graphic, but there's some really important stuff here. So if I show you this figure, this is a cutaway of our Earth. So up here, continents, there's the atmosphere and the ocean, all the way down to the center. You guys can sort of see, you can look at this in your notes, but that is actually the whole Earth. This is just a cutaway down to the center of the Earth at 6,300 kilometers or so. Well, first thing, let's say you're looking at your homework and let's say there's a problem that says, hey, draw me something that shows the layers of Earth all the way from the core to the atmosphere in both their chemical and physical forms. Maybe this is a good slide to pay attention to and what we're talking about. And what I mean by that is we describe these layers in two ways, chemically and physically. And that means, so let's start on the chemical side. Let's look at these layers. And there's three main chemical layers: the core, the mantle, and the crust. And they're chemical because they're made of different things. So again, that density stratification, you're going to get the heavier chemistry towards the center, the more dense, sorry, not heavier, more dense stuff, and then lighter as it moves up. So down here in the core, it's mainly iron, nickel, all right, so those heavy metals. And then you get into the mantle, and it says here ultramafic silicates. If you write that down, that's great. That just means they're silica-based rocks, all right? And this is like 80% of the Earth, all right, is this mantle. And then you get out here in the crust, and now it's a little bit lighter. So there's still silicates, all right? There's still actually silica oxide, so a lot of oxygen. So I know this is silly, but back to what we talked about, oxygen, don't think of that as oxygen, just think of that as an atom with protons, electrons, and neutrons. Well, step on the ground, a lot of that's actually oxygen. Anyhow, this isn't necessarily a chemistry lesson, but we have a couple different kinds. We have something called granite and something called basalt, and that's just difference. We'll go into this a little bit later, but the difference between the ocean and land crust, right? But that's crust. That's the stuff that we're familiar with. And of course, we have the oceans and the atmosphere. Physically, these are broken up a little bit more and a little bit differently. So in the core, so this whole thing, both of these are both the core, but we have an inner core and an outer core. And the reason we break them up physically is because while they are both that iron and nickel, the inner core is rigid. It's a solid sphere-ish of iron and nickel. And then this outside is molten. It is liquid metal, all right, outside of that. And then the mantle is broken up a little bit too. So we have a lower mantle, and that's mostly rigid, and that's because of pressure. So it's keeping that fairly rigid. But then this upper part of the mantle, still the same chemistry, is something called the asthenosphere. And that's not liquid, but more deformable, more plastic, if you will. But importantly, it's still solid. And then above that is something called the lithosphere, and that is very rigid, all right? And that encompasses the crust and actually that upper part of mantle that has turned to crust. So again, this is the way, I guess I shouldn't stand in front of it, this is the way the interior of the Earth looks, both chemically and physically, and you guys need to know this. Well, how the heck do we know what this looks like? We don't even know what the bottom of the ocean looks like. We can't see through there. And I'll tell you, we spoke last time about those sediment cores. Well, those don't go very deep. Those drill ships can't get down very far into the crust. So how do we know what this looks like? Well, you may have guessed it. It's something that we use all the time. We already know how it works, and that's waves. We can use waves just like we can use sound waves to see into the ocean. We can use waves to see all the way through Earth, and these are a special kind, and these are seismic waves. These are waves that come from things like earthquakes, seismic activity. When earthquakes happen, yeah, the ground shakes and it's very violent. In fact, we had an earthquake here a couple weeks ago. I'm not sure if you guys felt that or heard about it, but there was one. In fact, I think I was sitting on my deck and yeah, that was weird. And then I happened to see an email that there was actually an earthquake up here. But importantly, regardless of what's going on the surface, is that energy goes all the way through the Earth. So what we can do is we can set up stations, various places around Earth, and see what gets there. And the reason this is important is because the earthquakes, they do a lot of things, but we're going to focus on these three particular waves, actually two of them in particular, that happen. And we get something called internal waves, all right, these P waves and S waves that I'll talk about in a minute, that go through the Earth. And then we get surface waves that go around the Earth. So depending on where we're listening, these waves will arrive at different times and they'll have different properties. Let me see if I can show you what I mean. So again, this is the surface wave, right? And this is the stuff that causes havoc, right? Damages buildings, loss of property, all this stuff happens on the surface, shakes the ground very violently. However, they are just what they say. They're surface waves. They go around the Earth. So these aren't going to tell us a whole lot other than time, which is fine. But we really want these deep waves. We want these waves that travel through the Earth. And again, there's two main kinds. There's something called a P wave and an S wave. And you can sort of look at them and you can see that this S wave, looks a lot like a wave. This P wave, not so much. So we're going to learn a new type of wave. The one we've spoken most about is a transverse wave. In fact, I've made you guys go through this laboriously. Again, looking just like this. So picture these as both kind of slinkies, right? If you shake a slinky, we get a wave. And this is where the nodes are going up and down, right? And that energy is traveling along the slinky. Now we have something else called a longitudinal wave. And this is similar, but instead of, whipping a rope or something like that, you're pushing back and forth. And you can see here that wave moves along just like the transverse wave, but it doesn't go up and down. It's longitudinal. So similarly, like we did for a transverse wave, if we look at a bunch of particles moving in a longitudinal wave, and again, highlight one of these red ones up here, you can see that, yeah, these actually do move back and forth a little bit, but they don't move. The particles, all these little red ones, just stay there, and the wave is what moves, all right? Still that energy transfer. So very similar, just a different way that these waves act. So you can think of that as the R2 waves is the one that, the transverse wave, like we've already discussed, is our S wave, or shear wave. And then this other one, this longitudinal wave, is our P wave, or pressure wave. And the reason these are important is they have different properties as they pass through Earth. In the case of S waves are only capable of passing through solids. They can't go through liquids. So you'll see that, if we have an epicenter of earthquake up here, and those waves travel through, and oh, by the way, they do travel in a curve because there's still some density differences, right? Things tend to get more dense as you go. And we already know, based on the way sound waves work, that density plays a part. So they will curve. But they also won't go through liquid. And we already said that this outer core is liquid. So they'll stop and create this massive shadow zone. So if we have an earthquake up here at the top, and we're listening down here, we'll never hear the S wave or see it on a readout. We're not going to hear it. We're never going to see the S wave on a readout. But P waves will travel through both. They'll go through both solid and liquid, and they'll also have their own curves, right? They're going to curve depending on the change in density, depending on the change in state. So going from a solid to a liquid, they'll change a little bit. And we end up with P wave shadow zones as well because of that. So if you combine both of these, we get something that looks like this combination, earthquake at the top, epicenter. We can listen all around the planet, and depending on what waves arrive, we can start to build this picture of what's going on inside. Now, it's not going to just be one earthquake, but over time, just like everything else we do, we start to build these pictures. So we can start to know what happens inside. We can start to know about the size of the liquid part of the center of the Earth and the solid part. So that's how we know how the center of the Earth looks. And with all of this, we can make some really cool pictures, like this. Obviously, well, maybe not obviously, but the inside of the Earth is dark. It's not necessarily glowing like this, but it looks really cool. But it's fairly accurate. So again, here's our solid metal core. Here's our liquid outer core. Here's our most of the Earth. Remember, like 80% of the Earth is the mantle. And then we finally get up here to the crust. So that's it. Holy cow. We're almost to the end of the semester, and now we know from absolutely nothing, no space, no time, single point, 13.7 billion years later, we get this. And all the processes we discussed, right? We get our beautiful Earth and, well, okay, so this is oceanography, and I think there's something missing here. And yep, that's our ocean. Okay, so we don't know how the ocean got here. Now, we said the oceans formed about 4.5 billion years ago, but how did they get here? Well, let's go back and let's think about that original density stratification that we talked about. Well, in the same time that all these all this light stuff is coming to the surface and the heavy stuff going towards the center. Well, the lighter stuff are the gases, right? So the gases in the atmosphere and water vapor, right? Remember, water vapor is part of that atmosphere, so they're outgassing. So over millions of years, we have volcanic eruptions spouting gases into the atmosphere, including water vapor. And then it starts to rain, all right? And it rains for about 20 million years. Just this constant bombardment, more outgassing from the inside of the Earth, condensing in the atmosphere and raining down on the planet and starting to fill these voids and creating a shallow ocean around our entire Earth. Okay, add to that some bombardments by comets and asteroids, bringing a little bit more water, and we get our oceans. We get all this water on our planet, on the surface of our planet. And that gives us our beautiful blue marble that we live on. And again, all the stuff we're talking about. All right, well, that's where Earth came from. That's where atoms came from. I hope this was enlightening, and you can see now why it's so important, why I told you at the very beginning of class that oceanography is the study of everything. I'm pretty sure I haven't left a lot off. If I have, feel free to send me an email. I'll try and cover it in the next couple lectures. But another thing, too, I want to talk about this is, since we're talking about time and we're talking about change now, I want to show you another figure. So we had said last time that sediments are a record of time, all right? And this figure here is showing you that the black are the continents, and the color areas are ocean sediments, and they're based on age, all right? So I said that sediment record, if you remember, is age, because those things trickle down over time. And I want you to see here, the youngest ones are this red color, sort of here, and the oldest, this blue area, right up here, and a couple other spots. But there's a puzzle. Of course there's a puzzle, because how could I not have a puzzle? How would I ask you questions for you to answer if we didn't have a puzzle? So here, 144, 161 million years, this late Jurassic period. About here. Well, let's say, like right here, there's even older, maybe 190 million years. Well, we just said the Earth is like 4.6 billion years old, and the oceans are 4.4 billion years old. So the oceans were there collecting sediment at the beginning. And this 190 million years is nothing compared to that, right? Think about your timeline. That's only, what, like 2 inches, maybe a little more. So that's like here on, to my watch. That's it. That's how old the ocean floor is. Okay, well, why? So that's your first question. Why are the ocean sediments younger than the Earth, or just younger than the ocean, that much younger than the ocean, not even just a little bit? And second question is, why do they form this pattern? It's not like they're just scattered around. This is a very, here's the youngest, and as you move out, you get older and older and older. And then all of a sudden it stops. Same here. Youngest, older and older and older, until it gets to a continent, which continents have been around a lot longer than that. In fact, that's kind of how we know how old the Earth is. Some of that rock's been around for quite some time. So that's your second question. Why are they in this pattern? Why is the sediment so much younger, and why does it look like this? So I want you guys to think about that. Again, I much more enjoy just your thoughts. If you go look something up, look, I know the answer. You guys don't have to prove to me, but just think about it. What do you think? All the stuff that we've talked about, how is this possible? So I hope you're working on your last homework assignment or getting ready for that last exam. Again, this is that last push. You guys are working on those papers. I hope you're already writing. This is something you really need to get yourself into. I'm excited to see what you guys have to say. Your topics are amazing. Keep that all up. As always, contact me if you have questions or issues. Come to office hours for help. And I'll see you next time when we answer these questions. Why is the sediment so young, and why does it look so nice? I'll see you guys then.